All right, welcome to the Explainer. Today, we're going to tear apart how electronic circuits really tick. We're going to skip the heavy textbook formulas and build a real, intuitive feel for the components that power, well, everything. To really get a handle on this, we're going to use an analogy that's an absolute classic for a reason: the hydraulic system. Just picture electricity as water flowing through a set of pipes. And trust me, this simple idea, it's probably the best way to visualize what's actually happening inside those wires.
All right, first things first, voltage. In our water world, voltage is just pressure. Think about it. A taller tank of water creates more pressure at the bottom, right? Well, higher voltage provides a stronger push for the electrons. It's all about potential, the potential for work to get done.
So if voltage is the push, then current is the actual flow. It's not the pressure itself. It's about how much water or charge is actually moving past a point every single second. More flow means you've got more current. Simple as that. Okay, let's throw our first component into the mix, the resistor. And it does exactly what you think it does. It resists the flow. In our water system, this is just a skinny section of the pipe, a little bottleneck. Now, for the same amount of pressure, you're going to get less water flowing through that choke point. It's really the simplest, most fundamental way you can control current.
Okay, but things get really interesting when we bring in components that don't just resist flow, but actually store up energy. And get this, fight against sudden changes. I mean, these are the components that give circuits their personality, their dynamic behavior. So first on our list is the capacitor. Physically, it's just two metal plates with an insulator sandwiched between them. That means current can't just flow right through it. And its whole job is to store energy, but specifically in an electric field.
Okay, so how on earth does that translate to our water analogy? Well, imagine we sealed a flexible rubber sheet right across the inside of the pipe. Water can't get through it, but when you apply pressure, the rubber stretches and it pushes water out the other side. You see? That stretched out rubber is now holding potential energy, just like a charged up capacitor. Then this brings us to the absolute key takeaway for capacitors. Just like you can't instantly stretch that rubber sheet, you can't instantly change the voltage, the pressure across a capacitor. You can see it in the graph. The voltage has to build up nice and gradual. The bottom line? A capacitor hates sudden changes in voltage. It fights it. Now, every hero has a sidekick, or maybe a rival. And for the capacitor, that's the inductor. It's usually just a simple coil of wire. And it also stores energy. But instead of an electric field, it stores energy in a magnetic field that's created by the current flowing through it. So what's our water analogy for this thing? Well, picture a big, heavy water wheel. You know, a turbine, smack in the middle of the pipe. Because it's so heavy, it has inertia. It takes a real hard push to get it spinning. And once it's going, it really doesn't want to stop. And that mental image, it perfectly explains the inductor's #1 rule. Just like that big, heavy wheel can't just snap from 0 to full speed, the current flowing through an inductor can't change instantly. As you can see from this red line, it has to build up smoothly. An inductor fights tooth and nail against any sudden change in current. So you see this amazing, perfect duality we've got here? The capacitor, our rubber sheet, resists sudden changes in pressure, which is voltage. The inductor, our heavy water wheel, resists sudden changes in flow, which is current. If you can just nail down this one distinction, you're halfway to understanding almost any circuit out there. Okay, so here's a fun question. What happens if we decide to just ignore that rule? If we try to fight that inertia? What if that big water wheel is spinning like crazy and we just slam a gate shut right in front of it? Right? That wheel's momentum has to go somewhere, and it's not going to be pretty. It's the same thing with an inductor. You cut the current suddenly and its magnetic field collapses in an instant. All that stored energy has nowhere to go and bam! It generates this absolutely massive and, yeah, often destructive spike in voltage. This crazy effect has a name. It's called inductive kick. And it's not some kind of flaw. It's just what inductors do. Think of it like a water hammer in your pipes at home. You know that loud bang? It's the exact same principle, just with electrons. All right, so we can resist flow, we can store energy, but how do we actually control things? How do we direct traffic? For that, we need components that act like valves and gates in our system. Well, the simplest little gatekeeper we have is the diode. Think of it as a one-way check valve. Water can push its way through one way, no problem, just needs a little nudge.
But if it tries to go backwards, nope, the valve slams shut. It's a one-way street, pure and simple. But what if you need more than just on or off? For real precise control, we bring in the big gun, the transistor. This thing is arguably one of the most important inventions ever. It's not just a switch, it's a fully adjustable valve. The best way to think about it is like a super sophisticated valve, where a tiny little control pipe can move a plunger on a much bigger main pipe. With just a trickle of flow in that control pipe, you can completely shut off the main flow, open it all the way up, or fine-tune it anywhere in between. And this simple idea, this is the heart of everything. It's how we get digital switching on and off, and it's how we get analog amplification, making a small signal huge. Okay, so now that we have all our building blocks, let's see how they come together to create the amazing electromagnetic machines that run our entire world, from little tiny relays to massive industrial motors. Let's start with a relay. A relay basically looks at an inductor and says, hey, that magnetic field is cool, but let's make it do some real work. When current flows through the coil, it becomes an electromagnet, and that magnetic force physically pulls a lever, flipping a switch in a totally separate circuit. It's an awesome way for a tiny, safe electrical signal to control something big and powerful without ever touching it. Next up, the transformer. This thing is basically an electrical gearbox, and it's pure magic. You put an alternating current into the first coil, which creates a magnetic field that's constantly growing and shrinking. An iron core guides that changing field over to a second coil, and that pulsing magnetic field induces a whole new voltage in that second coil. There's no physical connection. It's incredible. And finally, let's talk about the motor. You've definitely seen what a motor does, even if you didn't realize it. You know when you're home and the refrigerator kicks on and the lights in the kitchen dim for just a second? Ever wonder what's causing that?
Yup, that dimming, that's the motor's inertia in action. A motor that's not moving is just like our stalled water wheel. It acts almost like a dead short, and it needs a massive rush of current to overcome that inertia and get moving. But once it gets going, it starts acting like a generator too, creating its own reverse voltage, a kind of back pressure that actually limits the current it needs. So the next time your lights dim, you're not just seeing a power sag. You are witnessing the raw physical inertia of electromagnetism at work, and that's the same fundamental principle that powers our entire world.